I want to go out, but it's so hot today.
Why don't you take an umbrella with you? It will protect you from the sun.
That's a good idea.
Susan, do you know how an umbrella helps you to protect against the hot sunlight on a sunny day like this?
Well, it blocks the sun's rays from reaching me.
How come the rays don't bend around the umbrella to reach you?
Not sure.
Light can't bend around objects. Light always travels in a straight line. The direction of light can only be changed through reflection. Want to find out more? Stay with us.
In this lesson, you will learn about the reflection of light from plane mirrors. At the end of this lesson, you will be able to demonstrate that the path of light is always a straight line. Explain reflection of light from plane mirrors. And identify the characteristics of an image formed by a plane mirror.
Let me show you some common examples that prove light travels in straight lines. Here, I'll switch on a torch. See? The light goes in a straight path to incident on the wall. It does not bend anywhere.
Hey, it's suddenly become nice and cloudy. Looks like it will rain.
Yes. Notice how the sun's rays are filtering through the clouds. You can clearly see the light in straight lines here.
Oh, yes, you're right. I can clearly distinguish the straight lines of light.
Can you think of any instances where you noticed light traveling in straight lines?
How about the red beam of light emitted by the laser toy gun my little brother plays with?
That's a good example.
Hey, what's this, Miss Sunshine?
What happened, Susan?
You had said that light travels in straight lines. Then, how is this beam of light coming back from the mirror?
Oh, that is because any shiny or polished surface, such as a mirror, changes the direction of light incident on it. Remember I told you the direction of light could be changed by reflecting it? Just like the beam of light incident on the mirror of the dressing table, let's direct the red beam of light from your brother's toy gun to incident on the mirror. Do you see what happens to the beam?
Oh yes, it changed direction, just like the beam I noticed earlier.
This happens because light incident on any smooth surface, like a mirror, bounces back into the same medium. This bouncing of light by any smooth surface, like a mirror, is called reflection of light. Notice another thing. Though light changed its direction when it was reflected from the mirror, it still travels in straight lines only. The path of light is never a curve. It is always a straight line.
In addition to the beam of light, I can see myself in the mirror as well.
Of course. That's what happens when you stand in front of a plane mirror. It is because of the light from your body reflecting from the mirror. Your reflection in the mirror is called your image.
So, the mirror will reflect an image of anything that is placed in front of it?
Rather than telling you, let me show you. Let's get that vase from the table there. Now, we'll place this plane mirror vertically on the table. Place the vase in front of the mirror, please. Can you see the vase in the mirror?
Yes.
That's the image of the vase in the mirror. Thus, in general, the impression of an object carried over and formed by light in a mirror is called the image of the object. In this case, the real vase in front of the mirror is the object.
My image seems to be becoming smaller as I move away from the mirror.
That's natural. As your distance from the mirror increases, the distance of the image from the mirror also increases.
Really?
Well, it can be proven easily. Let us place a scale perpendicular to the plane of the mirror on the table. The scale will help to measure the distance of the object in front of the mirror and also the distance of the image behind the mirror. Now, remove the vase and place a dice in front of the mirror. This will serve as the object in this activity. Move the dice closer to the mirror now.
Done. Now what?
Look at the image of the dice. What happened to the image when you moved the dice closer to the mirror?
Oh, you're right. I can tell from the reading on the scale that the image is now closer to the mirror.
That's right. And if you move the dice away from the mirror, the reverse will happen. The image of the dice will move away from the mirror by the same distance.
So, basically, the distance of the image behind the mirror is always equal to the distance of the object in front of it, right?
That's absolutely correct, Susan. So if you are standing at a distance of 1 meter in front of the mirror, then your image will be behind the mirror, at a distance of 1 meter from it.
Wow! So my image is at a distance of 2 meters from me when I'm just a meter in front of the mirror?
Right. Smart thinking.
Did you know? The fact that images in a mirror are located at the same distance behind the mirror as the object in front of it is widely used in architecture and interior decoration to make rooms appear bigger and brighter. When a mirror is placed along a wall, the room gets reflected in it. As the image is located behind the mirror at a certain distance, the room appears to be nearly twice its real size. Moreover, placing mirrors near lights, chandeliers, and table lamps helps to reflect the light over a larger area and make the surroundings appear brighter. Reflection in plane mirrors can also be used to have a lot of fun. Have you ever been to a mirror maze? A mirror maze is created using the principle of reflection in plane mirrors. This maze has several plane mirrors placed at fixed angles to each other. Whenever a person enters the mirror maze, he sees several images of himself and several passages in front of him. However, only one passage is real, while all the rest are just images. So a person ends up bumping into mirrors trying to find his way out.
Now let's play a small game based on reflection of light. Try to read what is written on Susan's t-shirt. A bit difficult, isn't it? Can you guess why? This is because what you just saw was Susan's image reflected in a plane mirror. And the words that you saw on Susan's t-shirt were left, right, inversed. Here, when you look at Susan directly, you can see that the message on the t-shirt is, "My name is Susan."
But what did you mean by left, right, inversed?
Left, right, inversed means that the image shows your right to appear as the left and the left to appear as the right. To give you another example, stand in front of the mirror and look at the hand on which you're wearing your wristwatch. Which hand are you wearing it on?
The left hand.
And which hand does it look like in the mirror?
It looks like I'm wearing it on the right hand. I see what you mean now.
Did you know ambulance is written left to right inversed on an ambulance, so that when the driver in a vehicle ahead looks into his rear view mirror, he can make out the word ambulance quickly and give way.
So, did you happen to notice any other characteristics of your image in the plane mirror?
Let's see. My image reflected in the plane mirror is left-right inversed, but it looks exactly like me.
Is it erect or inverted?
Erect, of course. And I guess it is the same size as me.
Absolutely right, Susan. There is one last important characteristic of plane mirrors that I want to show you.
Oh! What's that?
Remember the activity with the vase that we performed earlier? Let's set up that activity again. Place a white cardboard behind the mirror where the image appears. Let's see if we can capture the image on it.
We don't see the image on the screen. Let me try by placing the cardboard in front of the mirror. Still not getting the image on the screen.
That's right. We are not able to capture the image of the vase formed by a plane mirror on a screen. Images that cannot be captured on a screen are known as virtual images. So, you see, Susan, the image formed by a plane mirror is of the same size as that of the object. Left-right inversed. Erect. Formed behind the mirror. Formed at the same distance behind the mirror as the distance of the object in front of the mirror. And virtual.
Did you know? Based on the characteristics of an image formed by a plane mirror, it has been found out that the minimum length of a plane mirror required for someone to view their entire image is half their height. You'll learn why that happens in higher classes. This brings us to the end of the lesson on reflection of light. In this lesson, you learn to demonstrate that the path of light is always a straight line. Explain the reflection of light from plane mirrors. And identify the characteristics of an image formed by a plane mirror.
It's so dark. I can't see anything. Here you go.
Why do you think Tina couldn't see anything in the dark, even with her eyes open? Clearly, just the eyes are not enough to see. We can see only when light emitted by or reflected from an object enters our eyes. In this lesson, you will learn about reflection of light in plane mirrors and multiple reflections. At the end of this lesson, you will be able to identify the laws of reflection, identify the characteristics of images formed in plane mirrors, differentiate between diffused and regular reflection. Explain how reflected light can be reflected again. And demonstrate that sunlight is formed of several colors.
Hey, Tina, look here.
Ouch! What are you doing? Stop that!
James has figured out a way to direct sun rays towards Tina and is having fun teasing her. Hey James, Tina.
Hey,
I see you're having a good time.
yeah, this mirror game is cool.
Sure it is. However, do you know that this game uses the phenomenon reflection of light?
Well, I can definitely see he's using sunlight to tease me. So, what exactly is reflection of light?
The bouncing back of light incident on an object into the same medium through which it is incident on the object is called reflection of light.
Bouncing back of light?
Sounds confusing? Well, let me start from the basics. You are aware that light travels in straight lines, right?
Yes, we learned that in school.
The path along which light travels is called a ray of light. A ray of light is generally represented by a directed line segment. A collection of light rays is called a beam of light.
So, James was directing a beam of sunlight at me?
Yes, he was able to direct the beam using the laws of reflection. Light rays follow two laws of reflection. They are: the angle of incidence is always equal to the angle of reflection. The incident ray, the normal at the point of incidence, and the reflected ray lie in the same plane. However, that's a lot of jargon. Let's carry out an activity to understand the basic terms related to reflection and then prove the first law of reflection. We will need a plane mirror, a torch, a cardboard with a very narrow rectangular slit, white sheets of paper, pencil, adhesive tape, a protractor, and a set square.
There you go.
Good. Let's start with our activity. First, we fix the white sheet of paper on a table with the adhesive tape, so that a portion of the paper protrudes outside the table. We fix the cardboard on this sheet of paper. Then, we place the lit torch on the table and adjust it in such a way that the streak of light from the rectangular slit is seen along the white paper. The rectangular slit should be at the center of the light beam from the torch. Finally, we place a small strip of mirror in the path of the light ray. So, what do you see?
The light ray strikes the mirror and reflects in another direction.
Right. Something like what you were doing in your game. The light ray from the source of the reflecting surface is called the incident ray.
So in this case, the light ray from the torch hitting the mirror is the incident ray.
That's right. The light ray that bounces off the reflecting surface in another direction is called the reflected ray.
Are you referring to the ray that is reflected back from the mirror?
Exactly. Let's continue with our activity. Now, we draw a line on the paper along the mirror to mark its position. We mark some points on the path of the incident ray from the torch to the mirror. Similarly, we mark the path of the reflected ray. Now, let's remove the torch, cardboard, and mirror and join the points. Can you see where these lines intersect?
Interesting. The lines drawn along the paths of the incident and the reflected light rays intersect at a point on the line we drew to indicate the plane mirror.
The point at which the incident ray strikes the reflecting surface is called the point of incidence. Next, we draw a perpendicular to the line representing the mirror at the point of incidence by using a set square. This line is called the normal. Can you see how the other lines form angles with the normal?
Yes, both the reflected ray and the incident ray form angles with the normal.
The angle between the incident ray and the normal is called the angle of incidence. It is represented by the letter I. The angle between the reflected ray and the normal is called the angle of reflection. It is represented by the letter R. Now compare the angle of incidence and the angle of reflection using a protractor. Which one seems bigger?
Neither. Both angles seem to measure the same.
Correct. That's because the angle of incidence is always equal to the angle of reflection. Now let's look at the second law, which states the incident ray, the normal at the point of incidence, and the reflected ray lie in the same plane. We will slightly modify the setup that we used in the previous activity. Consider the portion of the white paper that extends beyond the edge of the table. Initially, you can see that the reflected light rays are on this portion of the paper, right?
Right. Now, fold the paper downwards, along the edge of the table. What do you observe? Can you see the reflected light ray on the portion of the paper that has been folded downward?
No, it is not visible now.
This is because the bent portion of the paper is now in a different plane. That is, the vertical plane. Thus, the plane of the reflected ray is different from that of the incident ray.
I get it. When the paper was spread straight along the surface of the table, it was on the same plane as that of the light ray incident on the mirror. The incident ray, reflected ray, and the normal, all the three were in the same plane. When the paper was folded, it went to a different plane, and so the reflected ray was not visible on that part of the paper. So that was the secret behind the trick James was playing on me?
Yes. Now that you know the laws, you can explore them and create tricks of your own. Tina is getting ready to go out. Hey, Tina, all set to go?
Yes. James and I need to decide on a project on reflection in plane mirrors. We have a lot of reading up to do.
Well, try observing your own image to begin with.
What do you mean?
When you look into the mirror, is your image erect or upside down?
Erect, of course.
How about the size of your image?
Looks the same size as me, also at the same distance from the mirror.
Yes, that's right. You could depict these properties of images in your science project. I'll give you an example. Let's take the letter R and see how its image is formed in a plane mirror. Place the letter in front of a mirror. We can treat this as an object. We know that light from objects reflects from the mirror. Consider a point X on top of the object and a point Y at the bottom of the object. Let MN represent the surface of the mirror. From point X on the object, consider a light ray incident on the mirror at point A. According to the laws of reflection, the angle of incidence is always equal to the angle of reflection. Observe the angle of the incident ray as it reflects and travels to the eye of the observer. from the same point X on the object, another light ray is incident on the mirror at point B, and the reflected ray travels to the eye. The two reflected rays from A and B are divergent. When extended behind the mirror, these rays meet at X dash. Thus, the image of the point X on the object is formed at X dash. Consider one more point Y on the object. A light ray from Y on the object is incident on the mirror at C, and the reflected ray travels to the eye. Similarly, another ray from Y on the object is incident on the mirror at D and is reflected to travel to the eye. Like the two reflected rays from A and B, the two reflected rays from C and D are divergent too, and when extended behind the mirror, meet at Y dash. Thus, Y dash is the image of point Y on the object.
That's a lot of rays.
Yes. It takes a large number of light rays to form a reflection of an object. So, as you can see, rays from all points on an object are incident on the mirror and reflected in different directions. That is, the reflected rays are divergent.
So, how do they form an image?
All these divergent rays are extended behind the mirror to form a complete image of the object.
So, the image is formed behind the mirror?
Yes. That's why images formed by a plane mirror cannot be obtained on a screen. Now let me show you another interesting thing about images in plane mirrors. Raise your right hand.
Okay, sure.
What does the mirror show you? Which hand is raised?
Oh, I see what you mean. In the mirror, it looks like the left hand.
Now, observe the image of the letter R formed during the activity.
Same thing, the left side appears to be on the right, and the right side appears to be on the left.
That is because of the phenomenon of lateral inversion. The image of an object that you see in a plane mirror is laterally inverted.
Hey, I can see my image in the window pane too.
Yes, the laws of reflection apply to all surfaces.
But then, why can't I see my reflection on other surfaces, like a wall for instance?
That's because light rays incident on surfaces like a wall are parallel, but the reflected rays are not. This happens because the surface of the wall is irregular. The reflection from such irregular surfaces is called irregular or diffused reflection. The reflection from a very smooth surface, like that of a plane mirror or a plane glass, is called regular reflection. In regular reflection, a set of incident rays parallel to each other is reflected from a very smooth surface as another set of parallel rays.
Are you saying that images are not formed on irregular surfaces?
That's correct. Images are formed due to regular reflections. Therefore, you are able to see your image in the window pane and the mirror, but not on the wall.
Are we able to see the stars and other objects in the sky due to reflection?
Yes, not all bodies have light of their own. Some bodies are visible only because they receive light from other objects and reflect it. Objects that have light of their own are called luminous objects, and others that don't are called illuminated objects. For example, the sun, a lit candle, and a glowing bulb are luminous bodies, while the moon, a table, and a book are illuminated objects. Tina is fascinated with the mirrored walls. She can see so many Tinas, she can't even count them.
Hey, Tina, I have a surprise for you.
A kaleidoscope. That's so cool. Look at all those beautiful patterns.
Aren't you curious about how all those lovely patterns are formed?
Is it due to reflection of light?
Well, yes. But a kaleidoscope goes a step further. It works on the principle of multiple reflections.
Oh, how's that?
Well, you can see innumerable reflections of yourself in these mirrored walls, right? A kaleidoscope utilizes the same phenomenon. Multiple images are a result of multiple reflections. That is, light rays are reflected many times across a set of mirrors. Some other examples of multiple reflections are found in mirror maze, saloon, periscope.
I'd sure like to see how my kaleidoscope works.
Well, let me show you through an activity. Let's take two plane mirrors and fix them in such a way that their edges form an angle of 90 degrees. Now place a small shell between the mirrors. What do you observe?
I can see a total of 4 shells.
Yes. One is the shell and the other 3 are its images. That's a result of multiple reflections across 2 mirrors.
But why only 3 images this time?
The number of images depends on the angle between the mirrors. The greater the angle between the mirrors, the lesser the number of images formed. Therefore, infinite images are formed when mirrors are kept parallel. Now let's see how this works in a kaleidoscope. You need 3 rectangular strips of mirror, each around 20 centimeters in length and 5 centimeters wide, a circular cardboard, a circular piece of ground glass, a plain glass disc, adhesive tape, chart paper, and some pieces of small colored glass.
Okay, we've got everything. Now what?
Join the 3 strips of mirror to form a triangle and fix them using the adhesive tape. Fix the mirrors into a circular tube made from the chart paper. Close one end of the tube with a cardboard disc which has a hole in the middle. Paste a transparent paper on the disc. Invert the circular tube. On the other end, fix the plain glass disc and put colored pieces on it. Then, close the end with the ground glass. The glass pieces should be small enough to move between the plain and the ground glass discs. Now, look through the hole on the cardboard disc.
Oh wow! It works! I can see so many colorful patterns every time I turn the tube. Hey, it's drizzling! And look, a rainbow! Isn't it beautiful?
Yes, the formation of a rainbow is a natural phenomenon. It occurs due to the dispersion of light. You know that sunlight, which is white, consists of 7 colors.
Yes, I know. We refer to the colors in the rainbow as Vibgyor.
That's right. We can reproduce a rainbow by passing a beam of light through a prism. You'll learn more about rainbows and dispersion of light in higher classes. This brings you to the end of this lesson on reflection in plane mirrors. In this lesson, you learned to identify the laws of reflection, identify the characteristic of images formed in plane mirrors, differentiate between diffused and regular reflection, explain how a reflected light ray can be reflected again, and demonstrate that sunlight is formed of several colors. We know that spherical mirrors are of two types, concave and convex. Specific terminologies are used in the calculations related to spherical mirrors. For instance, the center of curvature, or C, is the center of the sphere of which the mirror is a part. Likewise, the radius of curvature is the radius of the sphere of which the mirror is a part. The pole, or P, is the geometric center of the spherical mirror, while the principal axis is the line that joins the pole and the center of curvature. Moreover, the principal focus, or F, is the point on the principal axis. Let's now look at how the principal focus, or F, is determined. When a beam of light rays parallel to the principal axis is incident on the reflecting surface of a concave mirror, the rays converge at a point on the principal axis. This point is known as the principal focus of the concave mirror. Unlike a concave mirror, when a beam of light rays parallel to the principal axis is incident on a convex mirror, the rays diverge. These rays, when extended backwards, appear to diverge from a point. This point is known as the principal focus of the convex mirror. The distance between the principal focus and the pole is known as the focal length of the spherical mirror. It is denoted by F. Now, let's determine the relation between focal length and radius of curvature in the case of a concave mirror. In the diagram, P and F are the focus and the pole, while PF is the focal length of the concave mirror. C is the center of curvature. The distance PC represents the radius of curvature of the concave mirror. Consider a ray of light BP0 is parallel to the principal axis PC and incident on the concave mirror PP0. The concave mirror reflects this incident light, so the reflected light P0 R passes through the focus. Let's draw a normal P0 C to the mirror at the point of incidence P0. From the figure, we can say that angle BP0C is equal to angle P0CF, as these are alternate angles. Let this be equation 1. According to the laws of reflection, the angle of incidence is equal to the angle of reflection. So, angle BP0C is equal to angle CP0F. Let this be equation 2. From these two equations, we can conclude that angle P0CF is equal to angle CP0F. Since these angles are equal, we can conclude that triangle FP0C is isosceles. Hence, P0F is equal to FC. Let this be equation 3. If the concave mirror has a small aperture, then the point P0 is very close to the point P. Then PF and P0F can be considered as equal. Let this be equation 4. From equations 3 and 4, it can be inferred that PF is equal to FC. Let this be equation 5. From the figure, PC is equal to PF plus
FC. Based on equation 5, we can substitute FC with PF. Then the equation becomes PF is equal to half PC. Thus, the focal length of a concave mirror is half of its radius. Let's determine the relation between focal length and radius of curvature in the case of a convex mirror. Consider a ray of light BP0 is parallel to principal axis PC and incident on the convex mirror PP0. P0R is the reflected ray. In the diagram, P0N is normal to the mirror at the point of incidence P0, and the line extended backward to this normal is P0C, which is shown as a dotted line. From the figure, we can say that angle BP0N is equal to angle FCP0, as both are corresponding angles. Let this be equation 6. According to the laws of reflection, angle BP0N is equal to angle NP0R. Let this be equation 7. Moreover, angle NP0R is equal to angle CP0F because they are vertically opposite angles. Let this be equation 8. From the equations 6, 7 and 8, angle FCP0 is equal to angle CP0F. Let this be equation 9. From equation 9, we can say that triangle FP0C is isosceles. Hence, P0F is equal to FC. If the convex mirror has a small aperture, point P0 is very close to point P. So P0F would be equal to PF. By replacing P0F by PF, we get PF is equal to FC. From the figure, we can say that PC is equal to PF plus FC. By replacing FC by PF, we get PF is equal to half PC. Hence, we can conclude that for a spherical mirror, the focal length is half of its radius of curvature.
Most amusement parks have a hall of mirrors, a traditional attraction. Mirrors in these halls are often distorted into different curved, convex or concave shapes to give the participants unusual and confusing reflections of themselves. They may see stretched, shrunken or even bloated forms of their images. Sometimes the images are startling and at other times hilariously funny. Thus, the Hall of Mirrors can use properties of spherical mirrors to create an unusually funny experience for visitors. Of course, that's not the only area where spherical mirrors are used. You may be using spherical mirrors in your everyday life without being aware of it. In this lesson, you will learn about types of spherical mirrors and their uses. At the end of this lesson, you will be able to describe spherical mirrors, identify the characteristics of images formed by a convex mirror and concave mirror, and apply the mirror formula and sign convention to find out the relationship between distance of object and image from a mirror. A spherical mirror is made from a part of a hollow sphere of glass. In other words, it is a plain glass bulging inwards or outwards. Spherical mirrors are further classified as convex and concave mirrors. A convex mirror reflects light from its outer spherical surface and has a silver coating on its inner surface. Convex mirrors are usually used as rear-view mirrors in automobiles. A concave mirror reflects light from its inner spherical surface and has a silver coating on its outer surface. Dentists usually use concave mirrors to examine teeth. You need to be familiar with the terminology used in calculations involving spherical mirrors before you get into more detail. Let's start with the center of curvature. Center of curvature, C, is the center of the sphere of which the mirror is a part. Radius of curvature, R, is the radius of the sphere of which the mirror is a part. Pole, P, is the geometric center of the spherical mirror. Aperture is the surface of the mirror used for reflection. Principal axis is the line joining the pole and the center of curvature. Principal focus, F, is a point on the principal axis. This is the point where the rays in the reflected beam formed from the incident beam parallel to the principal axis converge. Focal length F is the distance of the principal focus from the pole of the mirror. Objects seen in the mirror are closer than they appear. You may have seen this warning sticker on the rear-view mirrors in your cars and bikes. These rear-view mirrors are actually convex mirrors. Rear-view mirrors help the driver to keep an eye on a large area behind the vehicle by providing a wide field of view. The behavior of the light rays reflected from a convex mirror varies based on the angle of incidence on the mirror. Let's take a look at a few cases of reflection of a light ray from a convex mirror, taking the example of a rear-view mirror. In the first case, incident rays are parallel to the principal axis. In this situation, the reflected rays appear to pass through the focus. In a rear-view mirror, incident rays parallel to the principal axis enables the driver to see the car traveling exactly behind his car. In the second case, let us consider incident rays directed towards the center of curvature. Here, the angle of incidence is 0. Hence, the angle of reflection too is 0. Thus, the reflected rays retrace the path of the incident rays and appear to pass through the center of curvature. This enables the driver to see the parking meter on the other side of the road. Next, look at incident rays that are directed towards the principal focus. The reflected rays go parallel to the principal axis. This is how the driver is able to see the traffic signal which the car has crossed. Finally, if incident rays strike the pole at an angle with the principal axis, the reflected rays also make the same angle with the principal axis. This helps the drivers of two cars traveling alongside to look at each other in the rear-view mirror of the car ahead. In concave mirrors, such as a dentist's reflector, the reflection of rays is somewhat different from that in convex mirrors. Concave mirrors help enlarge the images of faraway objects or view objects that you cannot directly see due to their position. As in convex mirrors, reflection of rays in concave mirrors also follows certain rules. If the incident ray is parallel to the principal axis, the reflected ray passes through the focus. If the incident ray passes through the center of curvature, the reflected ray retraces the path of the incident ray. If the incident ray passes through the principal focus, the reflected ray goes parallel to the principal axis. If the incident ray strikes the bowl at an angle with the principal axis, the reflected ray also makes the same angle. The focal length of a spherical mirror depends on its radius of curvature. Consider a ray Q parallel to the principal axis incident at point M on the mirror. This incident ray is reflected in accordance with the laws of reflection. When the reflected ray is extended beyond the mirror, it meets the principal axis at point F, which is the principal focus of the mirror. We know that angle I is equal to angle R by the laws of reflection. Angle I is also equal to angle MCF, as they are corresponding angles. Additionally, angle R is equal to angle CMF, as they are vertically opposite angles. Therefore, angle MCF is equal to angle CMF. Therefore, CF is equal to MF. If point M is very close to point P, that is, the linear aperture of the mirrors is very small, then MF is equal to PF. Therefore, CF is equal to PF. Also, PC is equal to PF plus CF. Or, PC is equal to 2PF, since CF is equal to PF. Therefore, R, the radius of curvature of the spherical mirror, is equal to 2PF. But PF is nothing but the focal length of the mirror. Therefore, R is equal to 2F, or F is equal to R divided by 2. Hence, in case of spherical mirrors, the focal length is half the radius of the curvature. When a beam parallel to the principal axis is incident on a convex mirror, its rays diverge. These rays, when produced backwards, appear to diverge from a point known as the principal focus. The image formed by a convex mirror is always erect, virtual, and diminished in size. The location of the object does not affect the characteristics of the image. Thus, as the object approaches the mirror, the image approaches the mirror too, but not proportionately. This is why the rear view mirrors of cars and bikes are made of convex mirrors. When a beam of rays parallel to the principal axis is incident on the reflecting surface of a concave mirror, its rays all converge at a point on the principal axis. This point is known as the principal focus of concave mirror. Unlike a convex mirror, the nature and size of the image in a concave mirror depends on the relative position of the object from the mirror. Let us examine the characteristics of the image of an object at different points in front of the mirror. When the object is at an infinite distance, the image is formed at the principal focus F. This image is real, inverted, and highly diminished in size. When the object is placed at a finite distance greater than the radius of curvature R, the image is formed between the principal focus F and center of curvature C. This image is real, inverted, and diminished in size. When the object is placed at center of curvature C, the image is formed at the same point, that is, at C. This image is real, inverted, and equal in size to that of the object. When the object is placed between the principal focus F and the center of curvature C, the image is formed beyond the center of curvature C. The image in this case is real, inverted, and magnified. When the object is placed at the principal focus F, the image is formed at infinity. This image is real, inverted, and highly magnified. When the object is placed between the principal focus F and the pole P, the image is formed on the side of the mirror that is opposite to the object. The nature of this image is virtual, erect, and magnified. Now, based on your knowledge of spherical mirrors, let's examine how these mirrors are used in amusement parks. The hall of mirrors that you saw earlier uses combinations of concave and convex mirrors to show funny, distorted images to the viewer. Concave mirrors are converging mirrors. They help us view enlarged images. Therefore, if you stand close to such a mirror, you will see a wider, fatter image of yourself. On the other hand, standing close to a convex mirror will make you appear thinner. With a set of such mirrors around you, you can see a variety of images of yourself, an undoubtedly interesting experience. The analysis of properties of images formed in convex and concave mirrors showed us that these mirrors present images that are either smaller or larger than the relevant objects. The ratio of the height of the image in a spherical mirror to the height of the object is called linear magnification. Linear magnification is denoted by small letter m. You can determine the size of the image reflected in a spherical mirror by using linear magnification. You can also compute magnification as the ratio of image distance to object distance. Thus, the ratio of the height of the image to the height of the object is equal to the ratio of image distance to object distance. Magnification can be unity, greater than 1, or lesser than 1. Magnification is unity when the size of the image is equal to the size of the object. When you look at your image in a plane mirror, it is of the same size as yours. Therefore, the magnification of plane mirror is unity. In other words, there is no magnification. Magnification is greater than 1 when the size of the image is greater than the size of the object. When the object lies between C and F of a concave mirror, the image formed is inverted, real, and bigger in size compared to that of the object. In this case, the image is said to be magnified. Thus, magnification is greater than 1. If the object is placed between F and P of a concave mirror, then the image formed is virtual, erect, and bigger than that of the object. Hence, in this case also, the magnification is greater than 1. Dentists use this situation to view the inner parts of a mouth with more clarity. Magnification is lesser than 1 when the size of the image is lesser than the size of the object. When an object is placed beyond C of a concave mirror, the image formed lies between C and F of the mirror. It is inverted, real, and the size of the image is lesser than that of the object. Thus we say that the image is diminished and its magnification is lesser than 1. In the case of convex mirror, irrespective of the position of the object, the image formed is virtual, erect, and its size is smaller than that of the object. Hence, in a convex mirror, the image formed is always diminished and its magnification is lesser than 1. Suppose an object is placed in front of a concave mirror. The distance between the object and the mirror is 30 centimeters. The focal length of the mirror is 10 centimeters. How will you find the position of the image? The object distance, image distance, and focal length in a spherical mirror are related. The mirror formula defines the relationship between these aspects. 1 divided by F is equal to 1 divided by U plus 1 divided by V, where focal length F is the distance between the pole P and the principal focus F. Object distance U is the distance of the object from the pole P of the mirror. Image distance V is the distance of the image from the pole P of the mirror. All distances are measured from the pole. The distances measured in the direction of the incident light are taken as positive. The distances measured in the direction opposite to that of the incident light are taken as negative. Try to apply the mirror formula in this problem. According to the problem, U is equal to 30, F is equal to 10. According to the mirror formula, 1 divided by F is equal to 1 divided by U plus 1 divided by V. Substituting the values for F and U in the formula, you get V is equal to minus 15.
Why are you slowing down, Dad? There is no vehicle in front of us.
Well, actually, there is a car coming up very fast right up that sharp corner.
How could you have seen that?
It's not magic. I noticed the car in the convex mirror reflector placed at the sharp turn there. Can you see it?
In this lesson, you will learn about spherical mirrors. At the end of this lesson, you will be able to describe the different types of spherical mirrors. List the uses of the different types of spherical mirrors. Identify and describe the difference between a real and a virtual image. And list the characteristics of images formed by spherical mirrors.
It's such a sharp turn. I couldn't see the car at all.
Well, that's why these convex mirrors are placed at such bends. They provide better visibility and reduce the risk of accidents.
Convex mirror? What's that? The only mirrors I know of are called plane mirrors.
We're almost home. Just let me park the car and I'll show you what I mean. A convex mirror is a type of spherical mirror. You're already familiar with plane mirrors, right? So, you know that a plane mirror has a flat reflecting surface that reflects light. Spherical mirrors are a little different. They have curved reflecting surfaces and are therefore also known as curved mirrors.
Is that why you have that ball in your hand? To explain the concept of spherical mirrors?
You're a smart kid. I'll show you how a spherical mirror is made from a hollow sphere. Before I show you how spherical mirrors are made, let me introduce you to the types of spherical mirrors: concave mirrors and convex mirrors. The name of each type of mirror is based on the reflecting surface. Now I'll show you how to make a spherical mirror. I will start by cutting this plastic ball into half. As you can see, I now have two hemispheres. Now, if I asked you to describe the two types of curved surfaces in each hemisphere, how would you describe them?
The inner curved surface and the outer curved surface.
That's absolutely right. The inner curved surface is what you would describe as concave, while the outer curved surface is convex. Here's some silver paint. David, since you like to paint, go ahead and paint the inner surface of one hemisphere with this paint.
I'm done.
Good. Now look into it. Do you see your reflection?
Yes, it's not really like my reflection in a normal mirror though.
That's because this is not a normal plane mirror. You just created a concave mirror.
I see. So, if the reflecting surface of a mirror is concave, it's called a concave mirror.
Okay, now paint the outer surface of the other hemisphere with silver paint.
Done. Considering the reflecting surface is convex, would this be a convex mirror?
That's right. You're getting better at this.
That was fun.
Remember, for an opaque spherical surface, the silvered surface acts as a mirror. So, a convex mirror will have its convex side silvered, while a concave mirror will have its concave side silvered. But here's another interesting thing. For a transparent spherical surface, if the concave surface is silvered and thereafter coated with red oxide, the mirror acts as a convex mirror. Likewise, if the convex surface is silvered and thereafter coated with red oxide, then it acts as a concave mirror.
Did you know? A convex mirror is also known as the fish eye mirror or diverging mirror. On the other hand, a concave mirror is also known as a converging mirror.
You already know that convex mirrors are used as reflectors at sharp turns and tricky corners. The use of these reflectors is not limited to sharp turns. These mirrors are also used in parking lots. A convex mirror provides a wide area of vision, thus enabling us to keep an eye on the traffic.
So the rear view mirror that you use in cars to see the vehicles behind you should also be a convex mirror, right?
That's right, David. Car manufacturers use convex mirrors as rear view mirrors in cars.
Did you know? Convex mirrors tend to distort the perception of distance. It is for this reason that most rear view mirrors are labeled with a safety warning. Objects in the mirror are closer than they appear.
This is really interesting. I had no idea that we use convex mirrors all the time.
Yes, it happens. We often fail to notice things around us. Let's test your powers of observation now. Try recollecting. Where else do you think you have seen a convex mirror being used?
Let me see. But of course, when I had accompanied you to the ATM, I noticed that there was a large mirror placed behind the machine. That mirror showed us everything happening behind us. That definitely must be a convex mirror.
That's a good example, David. Yes, convex mirrors are used in ATMs as a simple security feature, allowing the users to see what is happening behind them. Similarly, you can also find such mirrors in large supermarkets. Come here, David. Take a look at this.
Hey, what's that? A convex mirror on your cell phone?
Yes, it is a convex mirror to help camera mobile phone users to take a self-portrait. Try it out.
Wow, I had definitely not noticed that before. Convex mirrors are really very useful.
David is exploring various uses of convex mirrors. Meanwhile, let's recap quickly what you learnt about uses of a convex mirror. Convex mirrors are used as reflectors at sharp turns and tricky corners, in traffic as well as parking lots, rearview mirrors in cars, simple and handy security feature at ATMs, surveillance mechanism at supermarkets and stores, an aid to camera mobile phone users who click self-portraits. Did you know? Objects like thumbtacks, Christmas baubles and sunglasses act as convex mirrors too, though they haven't been specifically designed to act as convex mirrors.
Dad, didn't you say there are two types of mirrors? What are concave mirrors used for?
Figure it out yourself. Concave mirrors are primarily used to magnify an object.
I see. In that case, the mirror used by dentists to see an enlarged view of the tooth would probably be an example.
That's right. Good thinking.
And is your shaving mirror a concave mirror as well?
Yes, it is. A shaving mirror does provide me a magnified view while shaving.
Well, I don't think I can think of any more uses.
Here, let me help you. Concave mirrors are also used to focus sunlight for heating purposes in solar heaters or solar concentrators. You also see it being used as a reflector in flashlights and headlights of cars and scooters to give more visibility to drivers at night.
Let's have a quick recap of the uses of a concave mirror. Concave mirrors are used by dentists to magnify the tooth, for shaving mirrors, for solar heaters or solar concentrators, as reflectors in flashlights, headlights of cars and scooters.
So, spherical mirrors differ from plane mirrors due to their use and their reflecting surface. Are those the only differences between a spherical mirror and a plane mirror?
No. Let's see another difference. Do you remember if the image formed by a plane mirror can be captured on a screen?
No. The image formed by a plane mirror cannot be captured on a screen, and such images are known as virtual images.
Let's look at the type of image formed by a concave mirror. Let me place a concave mirror on a stand and then place this toy in front of the mirror. David, please place a white cardboard in front of the mirror. Good. Now, try and move the cardboard to and fro till you reach a point where you can see the image of the toy on the white cardboard. See, the image from the concave mirror can be obtained on a screen.
Oh, we were never able to obtain the image from a plane mirror on a screen.
Yes, in certain cases, you can obtain images from concave mirrors on a screen. This is in contrast to the virtual images formed by a plane mirror. Images that can be captured on a screen are known as real images. So, what do you think about the images that are clicked by your camera? What kind of images are those?
Let me see. Images clicked by a camera can be captured on the negative film, which acts as a screen. So they are real images, right?
Absolutely right. You're learning fast.
David seems to be catching up with the concepts really fast. Hello there. So, you have been learning a lot about spherical mirrors. Come, let me take you through an activity that will highlight the characteristics of images formed by spherical mirrors. David will help me with this activity. As you can see, David has placed a concave mirror on a stand on the table. David, now place the toy in front of the mirror. Keep it close to the mirror. Next, place a screen in front of the mirror behind the toy. Let us now observe the image formed. Notice that the image was not captured on the screen. Hence, a virtual image was formed. Also observe that the image is upright, that is, erect and magnified, hence appearing larger than the actual object. Now, slowly move the toy away from the mirror till you are able to obtain the image of the toy on the screen. How has the image changed? The image is now appearing on the screen. So, is it real or virtual?
Real, of course. Also, the image still appears larger than the actual object. It is now inverted. Shall I keep moving the object away to see what happens to the image?
Sure. David, go ahead. But don't forget to move the screen so that you can find the new position at which the real image is formed. So, how did the image change?
As I moved the toy further away from the mirror, the image formed continued as a real image and appeared inverted as well. However, instead of being magnified, the projected image appeared smaller than the actual object.
You mean it diminished in size?
Right. And yes, to obtain the image on screen, I had to move the screen closer to the mirror. As I continued to move the toy further away, nothing else changed.
So, the same characteristics continue to apply to the image formed when you moved the toy further away. That shows images formed by a concave mirror can be real or virtual, erect or inverted, and magnified or diminished. Let us now try to observe the images formed by a convex mirror. David, replace the concave mirror in the stand with a convex mirror. We will continue to retain the rest of the settings. That is, the toy will remain in front of the mirror while the screen is placed just behind the toy. Let us now observe the image formed. Notice that the image formed is virtual, since the image was not captured on the screen. Erect, as it shows the object upright. And diminished, as is the image obtained is smaller than the actual object. David, now keep moving the toy away from the mirror and observe the image formed. Are there any changes?
As I moved the toy further away from the mirror, I noticed that the image formed was virtual, since it did not get captured on the screen. Erect, as it showed the object upright, and diminished, as the image was smaller than the actual object. As I continued to move the toy further away, the same type of image that I saw earlier was formed.
That's good, David. So, you see that the images that are formed by a convex mirror are virtual, erect, and diminished. This brings us to the end of the lesson on spherical mirrors. In this lesson, you learned to describe the different types of spherical mirrors. List the uses of the different types of spherical mirrors. Identify and describe the difference between a real and a virtual image. And list the characteristics of images formed by spherical mirrors.